Um, Happy to introduce you to this great track called Deep Vision. And my name is Itamar Friedman. It says in the program that I'm from Visual Lead. Well, for a lot of ends, there is new beginning, and today I lead Alibaba Israel Machine Vision Lab. But that's put that aside, and perhaps I should explain a deep vision name for this track. So perhaps two reasons. First, deep learning for vision, but it's not only because of that. It's because in this session we're going to dive deep, try to understand deeply about different aspects of deep learning, machine learning, etc., with aspect to machine vision, but not only. And with regards to that, let me introduce you to the first speaker, Elad Hoffer. He's from the Technion, probably from the first to introduce deep learning into Intel. And lately in the Technion, during his studies, he's trying to shake some common practices and make us understand better and more deeply what we think today about deep learning in general. And without further ado, go ahead.
Okay. So thank you very much for inviting me, for the kind words. So I'm going to talk about rethinking common practices in deep learning. And as all of you are aware, deep learning work is evolving pretty fast these days. And there are still many questions that remain unanswered. So to make progress, we use many heuristics and intuition-guided decisions. And they often work. But as I'll show you, some of these may prove misguided. And I'll cover three of these misconceptions. First one is the impact of batch size on generalization. The second is early stopping and determining overfitting, or what is overfitting. And the third is the role of the last classification layer. So first of all, I'll talk about our recent NIPS paper called Train Longer, Generalize Better. And it deals with the so-called generalization gap, which I'll explain now. So first of all, why we need to train using large batches. So over the past years, we've seen an exponential growth in computational power and the amount of data available. In order to build larger and better models, we need to leverage this growth and ensure this compute power will be properly utilized. To utilize our hardware, we need to parallelize using bigger GPUs with many units and over many devices. For example, we can split our model between devices, also known as model parallelism. But a simple and perhaps more scalable way is to use data parallelism. So neural networks are commonly trained using SGD or one of its variants, in which the parameter vector W is incremented by averaging the per sample loss gradients across mini-batches. So since each gradient in the mini-batch is calculated independently using the same weight vector, this computation can be distributed between workers. Therefore, the most straightforward approach to parallelize is just to increase the batch size, and thus the training speed of neural networks. So unfortunately, it was noticed by practitioners over the years that using large batches of samples caused a degradation in the generalization of the final models. We examined this phenomenon in the common and widely used ResNet model, trained with momentum SGD over CIFAR-10 dataset. As can be seen in the figure, during training, validation error seems to plateau near similar values for different batch sizes, and it is not very clear why is there a large difference in the generalization error when the learning rate is decreased. This was further highlighted by Keskar et al., who noted that this generalization gap might be an inherent problem with large batch training, and that it persisted in models even when trained without any budgets or limits until the loss function ceased to improve. It was suggested that this is related to small batch updates being more noisy, which helps avoiding sharp local minima and reach flat minimas, which have better generalization. So since validation error plateaued and training error decays near zero, we searched for another state variable to inform us of the learning dynamics. We measured the distance traversed by weights over the course of training and found slight variation between batch sizes. Interestingly, small batch training reached a significantly larger distance from initialization compared to large batch. For example, a batch size of 64 reached almost 4 times the distance than a batch size of 2048. Since the curves for different batch sizes seem to have a suspiciously similar shape, we changed the x-axis from epochs, the number of passes over the data, to the number of SGD iterations. This caused an approximate data collapse, where all the curves fell nearly on top of each other, revealing a universal logarithmic curve. As we explain next, this observation helped us to close the generalization gap, and we'll later explain why this logarithmic behavior appears. So next we describe our experiments aiming to close the generalization gap. We performed our experiments using ordinary momentum SGD, as it usually exhibits better generalization than adaptive methods such as ADAM. Additionally, we used gradient clipping to avoid numerical instability. As the gradients are highest during the early steps of training, its effect is very similar to a warm-up, decreasing in the learning rate during these first steps of training. As mentioned before, there is a noticeable generalization gap between small and large batch size. For example, examining ResNet 44, you can see over 6% of degradation in the final accuracy. Our first step is to adapt our learning rate so that batch statistics will stay similar to small batch regime. We find that for our test case, a square root scale is appropriate so that the variance of weight updates will stay approximately the same across batch sizes. This can change depending on the ratio of the mean and variance of the stochastic gradients in the dataset. Gradient clipping ensures this scaling will not cause divergence in early steps of training. Making this adaptation, the validation accuracy improved considerably, but the gap still remains. Using these modifications, we found that now the distance from initialization is better matched across batch sizes. However, as the graph indicates, small batch training still reaches a significantly larger distance compared to large batch. This indicates that insufficient number of steps is performed with large batches. This is not surprising, as the batch size increases, there is a decrease in the number of weight update iterations per epoch. According to this observation, we adapt the training regime so that in all batch sizes we'll perform the same number of steps. In short, we train our model a longer number of epochs in each training phase. In this graph, you can see that for the large batch training regime, this caused a large number of iterations in what seems to be a plateau region over the validation error. As we hoped for, this completely closes the generalization gap, and we now can see that large batches can generalize as good and even better than small batches. For example, you can see in the figure a batch size of 4,096 with an adapted regime reached a better validation accuracy than the same model with a small batch of 128. We confirmed this finding for numerous datasets and models and find a similar effect, that when the number of iterations is fixed for all batch size, there is no apparent generalization gap. For example, we were able to train on ImageNet using the AlexNet architecture with a batch size 64 times larger, with better accuracy than the original small batch result. So one key question is why weight distances increase logarithmically. We suggest an hypothesis based on a physical property, that during the early phases of training, that is when the training error is still very high, we traverse a noisy landscape with noisy step approximations. This is known as random walk over random potential, where the landscape is modeled to have noise proportional to the gamma power of traverse distance. This phenomenon is also known to cause an ultra-slow diffusion, as described by Marineri over 3 decades ago. The weights are moving from their initial point at a logarithmic rate of power gamma. Recall we previously found similar behavior with gamma equal to 1. We then measured the standard deviation of the training loss and estimated gamma. As predicted by our model, we found that the gamma was indeed equal to 1. An informal explanation for this behavior can be visualized, in which for the particle to move a distance d, it has to pass a potential barrier of height d power of gamma. This requires an exponential time to reach a desired goal, and therefore the distance d traversed is logarithmic in time. So we consider this behavior as a possible explanation for the need for many gradient updates, as an exponential number of iterations is needed to reach areas that yield good generalization. To summarize our findings so far, in contrast to previous works, we observed that there is no inherent generalization problem when training with large batches. All that is needed is to adapt the training regime in order to achieve comparable and even better generalization. We suggest an explanation for the mechanism behind this phenomena, a random walk over random potential, requiring an exponential number of training iterations to reach a desired minima. Additionally, it turns out that the total wall clock time required to train a model can be reduced in some cases. Since the time our paper went public, several works continue to make progress in training large models with larger batches using ideas very similar to ours, experimenting with computational resources unavailable to us and more aggressive learning rate regimes proved to allow a dramatic wall clock decrement, with latest work allowing to train ImageNet model in as low as 15 minutes, which previously required several days to converge. We now bring our attention to an intriguing phenomenon. We appear to need many epochs to improve generalization in what may seem an overfitting regime, where the training error and training loss vanishes, validation loss increases, and weight norm diverges. Early stopping practice suggests we should not do that we should stop training when validation loss increases. And yet, the validation accuracy keeps improving, although very slowly. So we found that the validation loss increases, the training error and loss goes to zero, while the weight norm diverges. It looks like we are overfitting, but validation error seems to never stop decreasing. It seems like we should reconsider early stopping. How all of this makes sense? So in a more recent work, The Implicit Bias of Gradient Descent on Separable Data, we show that this happens even for logistic regression over separable data, or in other words, a single layer neural network with logistic loss. In this case, we prove that such behavior is related to the slow convergence to the maximum margin solution. This is also true for deep models under several strong assumptions. So in the case of logistic loss over separable data, we proved that our classifier vector W converges to the maximum margin solution, W hat, at a logarithmic rate. This means it converges to the same solution as an SVM. So this convergence is characterized in later steps in the increment of the weights norm, so that the training loss is affected by only a small fraction of the training data. While training loss continues to decrease and the norm continues to grow, the expected loss, estimated by the validation loss, increases at a logarithmic rate. This happens due to the fact that misclassification in our validation set, as demonstrated in this figure, are now inflict a growing loss as the margin norm increases, shadowing the loss inflicted by all other samples. So we should actually expect the validation and test loss to increase, even though the accuracy and generalization are still improving. So finally, I would like to focus on the role played by the final classification layer that is very commonly used in neural networks for classification. So this is a work to appear in iClear called Fix Your Classifier. So we will take a look on X, the representations that are fed to the last fully connected layer, which we'll call our classifier. In most neural networks, classification models, X is followed by an additional affine transformation to the space of possible classes. The matrix W is growing linearly in size with the number of classes, often reaching millions of parameters. Training is done using cross-entropy loss by feeding the network outputs through a softmax activation and then reducing the expected negative log likelihood with respect to the ground truth target. So this is very standard practice in training neural networks for classification. But as we all know, the final fully connected transform is a linear classifier. So the network learns features that are already separable at this point. The fully connected are also very notoriously redundant. They're easily compressed and easily discarded. So in our recent work, we suggest to discard the parameters of this layer altogether. In order to do so, we replace the weights of a fixed, the learned weights W with a fixed orthonormal projection denoted here by Q. As the weight rows have a fixed norm, we also restrict the representations X to reside on the n-dimensional sphere by normalizing by the L2 norm. Additionally, as the softmax function is scale sensitive, we introduce a temperature scaling parameter alpha. We can then minimize the adapted log likelihood loss as done usually. The fixed projection can also be replaced by a Hadamard matrix, having only plus and -1 entries. As this is a well-defined matrix with only binary precision, it can be easily generated, and multiplication by it can be replaced by simple sign and some reductions. Comparing fully learned classifier with a fixed classifier on CIFAR10 using ResNet, we find that although training error is lower with a learned classifier, both models achieve the same final validation accuracy. So you might argue that this is only a small-scale task with only a small subset of parameters removed, but the truth is we find this to hold in large tasks as well, even across common large ImageNet models. We see that using a fixed classifier yields negligible decrease in accuracy while removing a large portion of the number of parameters. A good example for this is that it happens even when in cases where the last layer holds most of the parameters. Okay, so in the case of ShuffleNet, most of the parameters are removed, but the accuracy almost is not impaired. So to summarize, large batch training the effect on generalization induced by large batch training can be mitigated and avoided. The fact that validation loss increases is actually expected. It does not mean that overfitting occurs. That means you should reconsider doing early stopping when you train models to classify. And finally, we find that linear classification layers may play a smallest role than previously thought. They were shown to have marginal effect and can be completely fixed for some cases. So thank you very much for your time. I'll gladly take any questions, and you are welcome to visit my page.
Any questions, someone?
Hi. Could you repeat again the reason why generalization isn't harmed when the validation error increases?
So we found that the fact that validation loss increases is just an artifact of the way we train networks using the softmax and exponential tail losses. So actually, it should be expected. You train on your data set, and at some point, your classification will stay approximately the same, and the norm will increase. So you should expect the validation loss to increase as well. And it does not mean that your model is not good anymore, or it fails to generalize, because as you can see, the classification error on the validation set can still reduce.
Thank you.
Thank you very much.